So yeah, the plan for today is to talk a bit more about this application I was telling you just not yesterday, I guess last week about the Markov chains. And then after we do that, I'll move into explaining why the duality theorem works the way it's supposed to work. Maybe give you like a sense of like what the proof is like, without getting into too many details, but still useful to kind of like have like at least some partial idea of what the proof is the way it is. Like the book has like actually like a nice explanation about it. If you have been reading the book, I'll recommend like some pages for those who are interested. Let's see. Okay, so actually let me first remind you the setup of the problem we were in discussing last time. So, and I'll copy paste like the picture um to to the news notes. But kind of like the idea was like a very simple model for like cell phone company where like you have two types of consumers. Um, like these ones were the ones on S1 represented those with a cell phone, and the ones on S2 are the customers without cell phones. And the idea is like by the end of a year or a month, whatever unit of time you're using, uh, 20% of those with cell phone will sell theirs and will become without a cell phone, and 60% of those without a cell phone will get one. So that's kind of like how the model is supposed to run, and kind of like every year it is the same rules. So by the end of the same year, by the end of each year, it's always like the same proportions that kind of like make the same economic decisions. Of course, it's like a very simplified model, but like it's like a fun model to play with because it's a cute application of this farkas lemma. You'll see how that I was mentioning last time. So I'll connect it to this farkas lemma in a bit. Uh, what I was saying is that, if you call like N1 and N2 like the initial populations, right? Then after 1 year, we did find a formula for how many people have a cell phone and how many people do not have a cell phone. And then what I was saying is that because kind of like the rules are the same after each year, you kind of can find a similar formula for the after like the populations after the second year. But if you wanted to go this about it this way, it kind of gets a little bit messy, like the algebra. So it's useful to kind of like describe it in a different way where you can kind of like see more of like you know, like the structure that's at play. So where did I put? Ah, here it is. Yeah. So, right, like what I was telling you last time is that you could try to figure this out using like a matrix. So that's kind of what I'll explain first, and then I'll show you like what the formula is. Um, so I told you like if you were interested, you could like try to find the formula, but if you didn't, don't worry. Like we'll work it out like now. So yeah, for example, what I got said is that after 1 year, the population after 1 year was like the initial population, then you lose 20% of that population, and then you gain 60% of the consumers without a cell phone. So, and similarly for the other one, after 1 year, um, you what how many people have no cell phone is the original number. Then you lost 60% of those without a cell phone, but then you gain 20% of those with a cell phone. Okay, so that is how the formulas look like after year one. Okay, and so now to kind of like find out like the formula in a nicer way, you just have to play with these equations, because the first one, if you factor out an n1 here, you get 1 minus 0.2 plus 0.6 and 2. And similarly, in the other one, if you factor out at n2, you get 1 minus 0.6 plus 0.2 and 1. So let me write this a little bit different. So let me put the n1 on the right side. Same, I'll do the same with n2. Okay. So what is 1 minus 0.2? Okay, that is 0.8, right? But what is 0.8 in this picture, in this diagram? That was P11. So you can replace the first coefficient with P11. So you get P11 and 1 plus, what is 0.6 in this diagram? It was P21. So you get P21 times N2. Okay. And it's kind of like similar stuff you can do for the other one. So what is 1 minus 0.6? Okay, 1 minus 0.6 is 0.4, but what is 0.4 in this diagram? Is P22. So like you just put P22 here. So times N2. And then what is 0.2 in this diagram? That was P12. Is that okay? So far, so good questions up to this point. Yeah. And hopefully that kind of makes it more clear that this is like two linear equations for like, you'll see like, because if you think about n1 and n2 as kind of like the starting numbers, they're being multiplied by some constants, so it's kind of like a linear combination. So let me write it in a system of equations format. So this is saying that n11 is P11 n1 plus P21 n2, right? And you have that n21 is P12 n1 plus P22 n2, right? And from there, if you think of a vector n to be like the vector of like the initial population, so you define like a vector n to be n1 and n2, then what that says is that n11 and 2 1 is P, is like the matrix P11, P21, P12, P22 times n1 and 2. And this is like after 1 year. Again, like the 1 here just means like this is after year 1. And this is like what we call like the matrix P. That's the probability matrix P. I guess sometimes it's called like a transition matrix. I think that's like the correct term for it, because it's giving you the probabilities for transitioning from one state to the other. Where you think of the states again, like the idea is like a random person, random customer can be into one of two states: cell phone, no cell phone. The probability, like, if you choose someone at random, there are certain probabilities that tell you what is the likeliness that you got one with a cell phone or without a cell phone. And this is kind of like all, and then their behavior is all that you need to know is how what their decisions will be for like by the end of the next year. So by the end of the year, so that's reflected by this transition matrices, by these coefficients. Is that okay so far so good? And once you have it in this very elegant matrix notation, then kind of like everything works in exactly the same as before. So after 2 years, by the end of 2 years, what should be the populations? that is what we call N12 and N22. But the idea is that it's essentially the same formula, but if you use the input from year one, like the populations from year one. So it would also be P with N11 and N21. Okay. But this one you can replace with the previous formula so that you get P times N1 and 2. So that means that after year 2, in terms of like the original populations, you get P squared. You square the matrix times the initial vector. And that's actually what's called like the Markov condition, because something is like a Markov process. That's like how it's called, where like in order to determine like the preset configuration, you only need to know what was immediately before it, and you don't care about what was like 2 or 3 states ago. So like what this is saying is like in order to know the population at time 2, you only needed to know the population at time 1. It's just that the population at time 1 can also be determined in terms of like the population at time 0. So like you can go back, but like you don't need it is like kind of like it is short memory, because it only matters like the immediately preceding state. You don't need to know like the entire history of the system to kind of like know what it's going to do next. So that's kind of like what makes it nice. And so after time t, after t years, it's the same, but you just raise the matrix to the power t. Okay. The populations are like the matrix to the t times n1 and 2. Is that okay? Now there's something that really, and we're getting close to like the connection to the farkas lemma, but there's something cool that happens here if you kind of like start numerically just by computing like the higher powers of the matrix. Let me see if I can show it to you this in Wolfram Alpha, because on Wolfram Alpha there's an option to compute like the powers of a matrix. Let's see if I had it here. Okay. So if you remember, like this was like the original matrix that we had, like 0.8, 0.2, 0.6, 0.4. Uh, if you notice, like these columns always add up to 1, because those are just like the probabilities. So like they're called sometimes column stochastic matrices. But anyways, like that doesn't matter for what I'm going to do next. So in Wolfram Alpha, like you enter the matrix, and this number just tells you what exponent you're using here. So that's where the 1 comes from. So for example, if you wanted the square of this matrix, you just put the number 2, right? And so when you square that matrix, you get 0.76, 0.24, 0.72, 0.28, right? And then the cube of this matrix gives you this. Okay. Okay, you could continue going, but let's take a higher power. Let's take like, for example, 7. Okay. And so you see, like they kind of like are getting closer and closer to some fixed values. They're not changing that much. So if you take a sufficiently high power, like could be like 12 or something like that. I mean, it's not quite per se like 0.75, 0.25. It's just like now, like I don't know if like it's like a bunch of like it's followed by a bunch of zeros first, so like you cannot really see it with this approximation. But essentially, what's happening is like as you take higher and higher powers, kind of like the matrix stabilizes, so it just becomes like asymptotic to like a fixed matrix. Which is another way of saying that the limit as t goes to infinity of the matrix exists. And what's kind of like cool is not only that, but also like the columns become the same in the limit. So that's kind of like something that happens with these matrices. So let me write that down because that's kind of like a nice property.
Why it like have a limit? Why it's not a loop?
Well,
So why is a stable point?
yeah, like to see, like, let me see if it's like there's like a good way to think about that. So, uh, if you had a loop.
Like, I mean, if you have a stable loop that doesn't, the number in it doesn't become less and less until some fixed point.
Well, the thing, let's see, because like the thing is like all these numbers, well, there's like a condition that I'll write that every entry should be like, strictly positive, right? But the thing is like, okay, if you square a matrix, right? Like as every entry is kind of like a product and sums of like the previous entries, right? All of these numbers are between 0 and 1, right? So when you're multiplying numbers between 0 and 1, they, right, uh like okay, you have to be careful, right? Because I mean, if it were just multiplication, they do shrink, right? But like you're also adding them, so I guess, but it is possible, right? Like from there that you could get something that would give you like a cycle, but I think it won't happen. I mean, like what I'm going to show is that um these matrices do have like an eigenvector associated to eigenvalue 1, and if that, which is so is fixed by this, and I think if that happens, I mean, I guess you could like could you still cycle like, yeah, I think I'll have to think about if there's like a good like way to like an easy way to see this, because at the top of my head, like you like obviously in the two case you can use brute force to kind of
Yeah.
like show it, but you don't want to do that like in general, right? So like it might you may need to like diagonalize it, or there is something about the eigenvalues. If you knew that the eigenvalues are always less than like 1 or less or equal to 1, like you could try to say something. But yeah, no, I agree that it's not obvious, like from what I have said, that like the limit would exist. Like I also have to I'll think about it, like there's like an easy way to explain it, and maybe mention it next time.
Thanks.
Mm-hmm. No, but that's like, but yeah, like kind of like the nice property is that if every entry of P is positive, and then the limit as t goes to infinity of P to the T exists, and moreover, in the limit, all the columns are identical. Let's call like that matrix P infinity for like the matrix that exists in the limit. All the columns are identical. So like for example, why I'm bringing this up because this is kind of like nice because of the following reason. So let's call like what so in this case that we're working with, P infinity is just like a 2 by 2 matrix, so it would have two columns, but the columns are identical. So let's just call it AB, AB, right? So the populations at infinity, kind of like the long-term behavior. Like it is actually in practice what you would care about, like if you're a corporation, like you might want to think, oh, like this settles down, right? And maybe there's like a point of stability point, like and you want to know long term, like what are the proportions of people who have a cell phone or don't have a cell phone. So that's kind of like an interesting thing to know, because like the thing is like, okay, when you say t goes to infinity, that sounds very intimidating because infinity, okay, obviously it's like larger than any number, but in practice sometimes like the convergence to these limit values can be pretty fast. So if you saw here already by t equals by the 11th power, basically all the numbers were already essentially the same. So like even if like even if a limit exists only at infinity, that doesn't mean that already like by the first few terms, like you're not like already close enough. Like like the convergence can be pretty fast. Like so that's why like this could mean that after a decade, after a decade, it's more or less as at equilibrium. You are at an equilibrium, like kind of like in economic terms. Um, so, but theoretically, it is at infinity. Like, so let's put here infinity, kind of like saying like the long-term behavior of the population would be the matrix P infinity times like the initial populations. So by the way, for like the next few classes, my goal will always kind of do like a mix of theory with applications. So I'll try to kind of like oscillate between like the two, because now we're at like the stage where like the class can you know we can kind of like combine the two. Like in this type of problem, I wouldn't ask anything too specific beyond like maybe give you like a diagram and ask you to read off like the probability matrix and other things of that sort, like the transition probabilities, maybe compute like the populations after year two or something like that, just to make sure like you understand that it's related to matrix multiplication. You'll see why like, the farkas lemma appears in a moment, but in this particular case, how do you do this matrix? What is the operation of here? So, there are two ways to multiply a matrix times a vector. As I said, you can do like the dot products between the rows and the columns, or alternatively, you can take a linear combination of the columns using the coefficients of the vector. So you can do n1 AB plus n2 AB, right? And since the vector is the same, that gives you AB times N1 plus N2, right? But N1 plus N2 is like the total population in the complete market, like so like just like the total number of customers. So here like N was like the total number of customers, like with or without cell phone. So that means that like at infinity, right? Like the nice thing about this result is that at infinity, the populations only depend, like, they don't depend on the how many people started with a cell phone or without a cell phone. It only depends on how big the market was and like, the value for this particular column, like, for the P infinity column. But it is independent of what N1 and N2 are, like separately. So it's kind of like saying that you could have started with whatever distribution you had wanted, like maybe 30% had like a cell phone at the beginning, 70% didn't have like a cell phone, and then it stabilizes to like a particular proportion, which is given by, you know, by by this column vector. Okay, so that means like at infinity, like the long-term sizes, like at infinity, how many people have a cell phone or don't have a cell phone is independent of like the initial populations. Or don't have one. Only depends on how many people were there in the market. Does not depend on the initial numbers of people with or without cell phones. On the initial breakdown of the market, which is kind of a cool actually if you think about it. It's like a very nice feature. So for the particular matrix that we were talking about, just to make it a bit more concrete, um, so for example, for our matrix P, what was the matrix that we had for our matrix? I think I had written it before. It was 0.8, and then 0.2, and then 0.4, 0.6. Right, like P infinity, like just numerically based on what we were getting from like Wolfram alpha, P infinity was what, 0.75? Yeah. So P infinity would be 0.75, 0.25, 0.75, 0.25. So and so like here, like the final population sizes would be 0.75 of N1 and 0.25 of N2. Which means that in the long term, 75% of the population would have a cell phone and 25% of the population would not have a cell phone. And it didn't, and again, it's so extreme that it could have started with 99% with a cell phone or without a cell phone, and it stabilizes because of the rules. Like, so it's kind of like that's what makes it interesting, because again, like if many things, assuming that you could approximate like a system by a Markov chain, which is like a useful first approximation to many problems, apply problems like that use probability theory. If you're trying to predict the long-term behavior of that market, then that tells you that you should aim, that your customer base, 75% will have a cell phone and 25 will not by the end of a sufficiently long amount of time, which in practice could be a few months or years. Like, that's the point. Like, it's not that it really would take an eternity for this to happen. Like, these things can stabilize pretty quickly. So that's kind of like the type of like thing that, uh, you would use this as. Oh, sorry, like it should have been N, like, oops, like it's big N. Right, because it's like just depends on like the total size, not the individual sizes that you started with.
Capital N because we're just taking that vector as just N, right? Capital N.
Well, capital, so like kind of like the idea was like in the way I wrote it, S1, S2 were the initial states, N1 and N2 were like how many people you started on each state, and capital N was just like the total number of people, which remains the same throughout the problem, right? Because like there's conservation of population, right? Like the population does not change from time to time. Like it always remains the same fixed population. So, but capital N is not a vector; it's just like a scalar. It's like a number. The little n as a vector, it was a kind of like the vector of initial populations. You see?
Right, so that doesn't apply here.
Right. Sorry, what did you say? That does.
That doesn't apply here, it's just capital. N.
Right. That's just with capital N. Correct.
But
Yeah.
we were getting that, that's what we.
Yes. Yeah. And then like the usual trick in probability theory, like it's like sometimes because of this, like you could like because maybe the like this then like the capital N doesn't really play a big role, right? It's kind of like a rescaling factor, right? So you kind of like can take it to be one or just divide both sides by N, kind of like to work with fractions, like the proportions, right? And so but just to like the idea is that you could have start like so like take divide both sides by N. So right, like this is kind of like what you interpret as kind of like the limiting fraction, right? Like that's the thing with probabilities. Like there are many ways to think about a probability. One convenient way of a probability to think about it is kind of like a proportion. So it's saying like what is a probability that if at random at infinity you chose like a person, what's the probability that they would have a cell phone, 0.75, 75% or 25. So like it's kind of like nicer to work with like fractions, ratios instead of like absolute magnitudes in probability theory. So, okay, so the idea is that you could like, what that mean, it would make sense to try to ask, and now this is finally like the relation with the farkas lemma. So question, okay, so yeah, so sorry, before I ask the question, so like because of this, like if you had divided by n on both sides, like if you normalize, then the formula that we found, I'll call it like this. So the formula that we had, this formula, oops, sorry. After rescaling by n, meaning that you divide both sides by n, what that tells you is that what is the probability at time t, what is the probability at time t that a certain number of people would have a cell phone? What's the probability at time t that a certain number of people would not have a cell phone? That was just p to the t, P1, P2, where P1 and P2 are now like the initial probabilities. So here now P1 and P2 is just like, N1 over N and N2 over N. And then kind of like, okay, now here comes like the definition. You say that a vector is a steady state vector if it's an eigenvector of the matrix P with eigenvalue 1. And you'll see why that definition gets used. So we say that P1, P2 is a steady state vector for the matrix P if uh, P times the vector P equals P. So you should compare this with like if you had, compare like in more traditional notation with AV equals V. That would, if you had written it in this way, I would say that V is an eigenvector of the matrix A with eigenvalue 1. Okay? So it is an eigenvector equation. It's just with a slightly different notation than the one that you have seen before, right? So P is an eigenvector of the matrix with of the matrix P with eigenvalue 1. That makes sense. And like the reason why a steady state is kind of cool is that if you have like a vector like that, then the probabilities are time independent because that means that doing P multiplied by P does nothing to the vector, right? So in this formula, P to the T like does nothing to it because these are just P times P times P times P, but each P does nothing to the vector. So the idea is like if you start the population with the probabilities of the steady state vector, the populations remain fixed. It's like an equilibrium point. Like they don't cycle. Like, I mean, maybe this is related to your cycle question, right? Like they don't like at that particular vector, nothing changes, everything gets static. So I guess that's why, like, in a sense, like maybe like you cannot have like a cycle of power, um, but so at a steady state, like, P squared P is P times P, which would be P times P, which would be P, and all power like and higher powers do nothing, and same for higher powers. P to the T equals P. So if you start like the market with those probabilities, like with the initial populations having those probabilities, then nothing changes over time. Like the market's kind of like starts on equilibrium, stays in equilibrium. It's like an equilibrium point, kind of like in terms like of economics. And in fact, what we're saying like before is that if you start at any other point that's not in the equilibrium, it kind of will approach this point like as time goes by. So everything is kind of like if you start outside of equilibrium, like it is approaching equilibrium because like the limit at infinity existed and all those properties that I mentioned before. Okay, so and this is finally where we get to this farkas lemma that I mentioned last time. My claim is that every matrix of this form will have a steady state vector. That's what I'm going to prove now. So my claim be like of like the type from above. Okay, so how do you do this? This is kind of like the fun part. So let's see how does this work? And kind of like a nice application of this Farkas lemma. So what do I want to show? Okay, so first like I want to kind of like return to like a more traditional notation so that we recognize it a bit better. So call X P, okay, just to make it like easier for us to kind of like think in the terms of like previous terms like that we have been using, right? So instead of like calling the vector P, which is like the natural concept in probability, right? Because it's like a probability vector. In fact, I'll tell you more about that later, because the other application that we'll talk about this is to game theory once we have the full duality theorem. But like this is what you would call like a probability vector because every entry represents like a probability. So they're non-negative numbers that add up all to one, okay? So this is how you would actually refer to it, but like just to kind of like connect it to what we have been saying before, like the name for our vector has always been x. So I'll call it like x instead of p and x1, x2 instead of p1, p2. But it's literally the same thing that we're talking about. Okay. So what does it mean to be an eigenvector? Like, you want to show that the system that this has a solution, right? Okay, now I don't know how much you remember about eigenvectors. There's not much that you had to use here, but like there was a trick when you were trying to find eigenvalues, eigenvectors. There was like this characteristic polynomial and all this stuff, like you may recall. But the idea is like let me just move x to the other side, okay, and then every vector is secretly multiplied by the identity matrix if you want. So you can write this as P minus the identity matrix times X equals 0. And so because P was, P11, P 12, P21. Oh, sorry, I kind of like mixed the names here. Yeah, the weird thing is like the convention in this case is like the opposite of the usual convention that we use. for the entries. Then what you're trying to show is that this system has a solution. So, if you remember when you would find eigenvalues, you would multiply by lambda here. So you would have like minus lambda to take the determinant of the matrix at it equal to 0, and they would get like a quadratic equation, and that's how you would find the eigenvalues of a 2 by 2 matrix. Like was like this characteristic polynomial. But here, like the eigenvalue has to be 1 because like a steady state has eigenvalue 1. Oh, sorry, and I forgot like the off diagonal matrix entries. Is that what you were looking at? Yeah, like oops. This is not, yeah, this is not a diagonal one. Sorry about that. No, this looks better. Okay, good. Whew. But yeah, like in general, what I was saying is that because the eigenvalue is 1, there's why you see a 1 here. If it had been eigenvalue lambda, you would put minus lambda, take the determinant of that, set it equal to 0, right? And um, that's how you would find the eigenvalues in general. So this is all good. This is great. The thing is that you do want to, add a kind of like add explicitly like the condition that this should be a probability vector, which means like these two entries should add up to 1 because like a probability vector, like the probabilities have to add up to 1. So in fact, what we're going to do, like we also have to keep into account. So we have another condition, the condition that x1 plus x2 should be 1, right? Because probabilities add to 1. That's important. So like, you can add it as an extra equation to, to this matrix. So like the way I'll write the system is that we work instead P11 minus 1, P21, P12, P22 minus 1, and then 1, 1 times x1, x2 equals 0, 0, 1. So just like imagine this as like an extra equation that I read off like the coefficients. The coefficients are 1 and 1, and it's supposed to be 1. So that's what that kind of like incorporates the condition that that incorporates the condition that the probability should add up to 1. Okay. Is that making sense? Okay, and we're getting closer to the notation that we have used in the course because, okay, this is the vector x, right? This is the vector x. Okay, this is the vector b. Usually that's what we would call b. Right, so now I'm going to write everything in a way that looks more familiar. And this is a vector a. Okay. So asking, what are we finding here? That asking for this for there to be an eigenvector is the same as asking for this system to have a solution. Okay, they are like the same thing. Again, there's an extra condition that usually eigenvectors do not have because here we do have like we do want the entries to add up to 1 because of the probability interpretation. Okay. And also what we want is like we also wanted like each of these entries to be non-negative because like probabilities are non-negative numbers, right? So what we're trying to, since also x1 and x2 have to be non-negative, since probabilities can be negative. And so So what we're trying to show, so we're trying to show that x greater or equal to 0 and ax equals b has a solution. And now this does look a lot closer to what we have been talking in the course, right? Like this looks like similar. And in fact, like, like one of the other reasons why I wanted to do this example, like in a lot of detail, is because usually in these math classes, like the biggest problem sometimes is just to know how to understand the notation that you see here with the notation that you'll see outside the class, right? So just connecting the dots and how things are labeled, in other courses, like, or other contexts, that's one of the biggest bridges, like, that you have to create to kind of like understand how to use things in a different, it is literally the same techniques, but sometimes like the letters usually, or the symbols that you use in another context are adapted to that context. So, like you will call P1, P2 for probabilities instead of X1 and X2. And these seem like small things, but like sometimes that prevents like from understanding what's going on, because you need to kind of like adjust it to that context. Um, okay, and now my claim is that this is essentially the type of thing that the Farkas lemma from last time said. So I'll just let me go back to the previous slide to just show you that literally that's what we were talking about, and I'll kind of copy what we were discussing like last time. So what I was saying like last time before we started this discussion was like this Farkas lemma. Where did I write it? Right. So the Farkas lemma was like basically what it said is that only two things can happen. That you can have like a solution to this system with a condition that the coefficients are not negative, which is kind of essentially what we are in right now. We're trying to look at a solution to this system with a non-negativity condition. And so either this happens, which geometrically you could interpret as saying that the vector V was a combination of the columns of the matrix A. So it was in the cone, it was in the cone generated by the columns. Or if that doesn't happen, right? If that doesn't happen, what that means is that you can separate the vector B from the cone by a hyperplane. That's what the Farkas lemma said. Only those two possibilities occur. So in this case, because I want to show that this occurs, so the Farkas lemma what says is that you have to show that this is impossible. Once you know that this is impossible, that forces this condition, and then that will tell you that there's a solution. So it's like a very clever, like not like an obvious like application of the lemma if you think about it, because it has like this like application to probability there. That's why I like it. So like so it's kind of like a proof by contradiction. So because geometrically what I want to show is that so I want B to be in the cone of the columns of A. Right, so like again, I'll kind of do it for this case. Like there are only two columns, right? Uh, let's call these columns A1 and A2. So you have like A1 and A2. This is the first column. This is the second column. This is like how the cone looks like. By the way, I already wrote some problems over the weekend for you to work on. I will post them tomorrow. I just wanted to add some other stuff, but I do want you to have like some problems to start working on. So I'll post them tomorrow and I'll tell you which ones to look at. But it's like useful to kind of like, because this like the topics that we're on right now, they do kind of like require some more like getting used to than the simplex method stuff. The simplex method is just like an algorithm, like, but these ones like have more like maneuvering required because like they're more clever like applications of like the theory we have discussed. So this is what I want. Okay. So by the Farkas lemma, what I will show is that the other configuration is impossible. So by Farkas, I will show that the other option is impossible, that the other option can happen. So what was the other option? The other option was where you have like the cone, right? But it is being separated from the vector B by a hyperplane. So maybe let's put it like this. Here was a hyperplane. So like again, this is why this is called like a separation theorem, because literally saying that if the system has no solution, then you can separate them. Um, and as I mentioned before, when you separate the system, you can, to specify a hyperplane, you have to specify the normal vector, right? And I'll call strategically the normal vector y in this case. So y is a normal vector. Notice that the columns, how many entries do the columns have? The columns have 3 entries, right? And the vector B has 3 entries. So all of this is in R3, actually, believe it or not. So like it's actually 3-dimensional problem. Like, we're in 3 dimensions. So this is all living in R3. So this is in R3. And so this vector, because it's in R3, has 3 entries, y1, y2, y3. So what was like the separation condition? Kind of like the idea is like these 2 vectors are on this side of the plane and the other vector is on the other side, which can be written in terms of the dot product, because if these 2 vectors are on this side of the plane, that means that their angle with the normal is kind of like acute, so the dot products were positive. And if this other vector is on this side of the plane, that means that the angle between them is obtuse, so like the dot product is negative. So what that means is that A1 dot y is positive, A2 dot y is positive, and V dot y is negative. But let's just write what everything is here. Like B was 0, 0, 1, if I'm not mistaken, right? And then let's see. And then the first column was P11 minus 1, P12, 1. And the second column of the matrix was P21, P22 minus 1, and then 1. So let's oh well, I guess they should be like I think they can be just like greater or equal to 0, actually. That's fine. Like this inequality won't be a problem. Yeah, like, but one is like strictly positive and the greater or equal, and the other is negative, strictly negative. That's fine. Because one of the vectors could be of the cone could be literally perpendicular to it. So like the cone kind of like opens, but that's okay. Like, so the first dot product gives you P11 minus 1 times Y1 plus P12 times Y2 plus Y3. So that has to be greater or equal to 0. Then the second dot product gives you P22 times Y1 plus P22, sorry, P21, like the first one should have been P21 plus P22 minus 1 times Y2 plus Y3 greater or equal to 0. And the last dot product, which is this one. What is the dot product between these two vectors? That just gives you that Y3. Like, well, it gives you 0, Y1 plus 0, Y2 plus 1, Y3 is less than 0. So that means that Y3 is negative. Like that's what like the last one says. But okay, is that making sense? Okay, and we're almost there. We just have to simplify this a little bit because what is P11 minus 1? Okay, if you look at this P11, sorry, just to go back for a second. P11 is like the first entry in this column, like the first entry in the first column. So these two numbers have to add up to 1, right? These two numbers add up to 1 because they're probabilities. And then, so if the sum is 1, then like P11 minus 1, that just gives you minus P12. So this gives you minus P12. Like, so here, like, what I'm using is that P11 plus P12 equals 1. And that also P21 plus P22 equals 1. Like, because the probabilities add up to 1 of each individual column of the matrix. So you get this. And the last one just says that Y3 has to be negative. Okay, and then we're almost there. What I'll do now is just factor out. So I'll factor out the P12 in this first one, and I'll factor out the P21 on the second inequality. So you get P12 times Y2 minus Y1 plus Y3 is greater or equal to 0. Then you get P21 times Y1 minus Y2 plus Y3 is greater or equal to 0. And you also getting that Y3 is negative. Okay. So let's see what's happening here. This is like enough because let's see what occurs. I don't know what the values for Y1, Y2, Y3 are, but like there's some possibilities. So one possibility is for like the Y1 to be equal to Y2. So let's just look at the cases. So case Y1 equals Y2, right? So if that happens, then the first inequality says, for example, that Y3 is greater or equal to 0. So let's call them A, B, C. Then A says that Y3 is non-negative, which contradicts C, right? It's impossible because Y3 should be negative, which violates C. Is that okay? Is that make sense? Okay, so definitely these two numbers cannot be the same. Y1 cannot be Y2. Then what else could happen? It could be the case that Y1 is greater than Y2. So what happens there? is strictly greater. So if y1 is greater than y2, that means that this difference is negative. Then y2 minus y1 is negative, right? And so in A, we would get P1 times something negative, right? Plus a negative number is greater or equal to 0, which is also not possible, right? So this is not possible. And okay. And what else could happen? It could also happen that y2 is greater than y1, right? If y2 is greater than y1, now I look at the other inequality, then y1 minus y2 should be positive. Sorry, y1 minus y2 should be negative. And so in B, what do you get? You get P21 times something negative plus a negative number. It should be greater or equal to 0, which is not possible. Okay, so all the possibilities fail. All the possibilities fail. So the conditions have, so what that means is like the condition for this vector to be separated from the cone cannot happen. So the vector cannot be separated from the cone. And by the farkas lemma, what that means is that the B is in the cone, which means like the system has a solution. And by farkas, B is in the cone. So there's a solution. Which means that there's this like eigenvector. So there's like a steady state exists. So probably the way I would ask you this is kind of like give you like a probability matrix and then just like set up by Farkas lemma what you need to show would be impossible. I wouldn't ask you to show that it's impossible because like it's like a little bit too tricky. But I would give you like a matrix, a P matrix, and be like, okay, according to Farkas lemma, what do you have to show is impossible to say that there's like a steady state? Something like that's doable. Like, it's just like understanding what the Farkas lemma says. So I think that's fair. But yeah, besides that, like, I think like going through all these cases, like it's a little bit too tedious. So it's more like, like the other one would be fine. I'll add that as a problem, so that to the PDF so that you have like an idea of what I mean. And also like maybe give you like a diagram, like so that you read off the transition coefficients, like read off the matrix. So I would probably give you the diagram, you extract the matrix, and then use the forecast lemma to say what would you need to show is impossible so that you can prove like the existence of the state vector. I like the steady state vector. I think that's kind of like a nice problem to have. It doesn't because it's just like setting it up. You don't have to do anything after you set it up. Okay, so let's finish here, and then like on Wednesday I'll tell you this duality theorem. Um, Maybe I'll give you like a very quick idea of why it works the way it does. but I don't want to get bogged down in like a long proof. And then I'll give you like an application of duality. I'll mention some stuff about duality and like what uses there is for it. Okay, but yeah, I think that's like a good place to stop.